there is a boundary surrounding us. Not a wall. Not a barrier made of anything physical, no membrane, no edge of matter, no place where the universe simply stops. It is subtler than that, more fundamental. A horizon like the horizon at sea, which is not a thing but a limit of what can be seen from where you stand. From where we stand on a small planet, in an ordinary galaxy, at this particular moment in cosmic time, there is a sphere of space from which light has had time to reach us. The universe is approximately 13.8 billion years old, and light travels at a finite speed. These two facts together define a boundary beyond which we cannot see, cannot detect, cannot receive information of any kind. Everything within that boundary is called the observable universe. Everything beyond it is not hidden from us by distance alone, it is hidden from us by time. The light from those regions simply has not had long enough to reach us. It is travelling toward us, some of it, at this very moment, but it will not arrive for billions of years, if the universe exists long enough for that. What lies beyond the observable universe, beyond our cosmic horizon, is one of the deepest questions in all of science and philosophy. And the honest answer is, we do not know. Not with certainty. Not with the direct observational evidence that anchors our confidence about everything within the horizon. But we are not entirely without ideas. Physics, mathematics, and careful reasoning have something to say about what the darkness past our horizon might contain. And what they say is in the most patient and wondering sense of the word extraordinary. Tonight, we explore the beyond, calmly, carefully. With the honest acknowledgement that we are, for perhaps the first time in this series, speaking of things that no instrument has measured and no observation has confirmed. What lies beyond the observable universe should not terrify us, but it should fill us with something very large. If you love exploring the cosmos, a like and subscribe would mean the world to us. Let's begin. Before exploring what lies beyond, we need to understand precisely what the observable universe is and is not. Because popular descriptions often simplify in ways that introduce subtle misunderstandings that are worth addressing from the beginning. The observable universe is the region of space from which light has had time to reach us since the Big Bang. Light travels at a finite speed, approximately 300,000 kilometers per second. The universe is approximately 13.8 billion years old. If we lived in a static universe, one that was not expanding, the observable universe would therefore be a sphere roughly 13.8 billion light-years in radius. But the universe is not static, it is expanding, and this expansion has been occurring throughout the entire history of the cosmos, including while the light that is just now reaching us was travelling toward us. The regions of space that emitted the most ancient photons we can detect were, at the moment of emission, much closer to us than they are today. They have been carried away from us by the expansion of space itself, while their light travelled toward us. The result is that the observable universe has a radius not of 13.8 billion light-years, the naive calculation, but of approximately 46 billion light-years. This larger number reflects the current distance to the most remote regions whose ancient light has only just now reached us, accounting for how far those regions have moved away from us during the billions of years their light was in transit. The observable universe, therefore, contains a sphere of space, centered on our location, approximately 93 billion light-years across. Within this sphere there are an estimated 2 trillion galaxies, or, by some more recent analyses, potentially more. Each galaxy contains billions to trillions of stars. The number of stars in the observable universe is estimated at perhaps 10 to the power of 24 or 1, followed by 24 zeros. And beyond the edge of this sphere, beyond the 46 billion light-year horizon, the universe continues. We simply cannot see it. The cosmological horizon, the boundary of the observable universe, is often misunderstood. It is worth spending some time on what this boundary actually is, because the nature of the boundary determines what we can and cannot say about what lies beyond it. The horizon is not a place where the universe ends. The universe does not end, at least not at our horizon, and possibly not anywhere. The horizon is a place beyond which we have not yet received any light or information, because the finite speed of light, combined with the finite age of the universe, means that information from those regions has not had time to reach us. This has a crucial implication. The horizon is observer-dependent. A civilization in a galaxy 1 billion light-years from us has a different observable universe than we do their horizon, is centered on their location, not ours. The regions of space they can see that we cannot, and the regions we can see that they cannot, are both equally real parts of the universe. The horizon is a feature of observation, not a feature of the universe itself. Moreover, the horizon changes over time. As the universe ages, light from more distant regions has more time to reach us. In principle, our observable universe should be growing new regions falling within our horizon as their ancient light finally arrives. However, this is complicated by the expansion of the universe. The universe is not merely expanding, it is accelerating in its expansion. Driven by dark energy, the rate of expansion is increasing over time. This acceleration means that the most distant regions are receding from us faster and faster, and some regions that are currently beyond our horizon will, because of the acceleration, never enter our observable universe. They are receding faster than light can bridge the growing gap. This means our observable universe has, in a specific technical sense, a permanent horizon, not just the current observational limit, but a boundary that certain regions will never cross. The universe beyond our horizon is not just temporarily inaccessible. Some of it is permanently inaccessible. This is the true nature of our isolation within the cosmos. Given that we cannot observe beyond our horizon, how do we say anything about the size of the universe as a whole? What evidence constrains our thinking about what lies beyond? The primary observational tool is the cosmic microwave background, the faint afterglow of the Big Bang that pervades all of space. Released when the universe was approximately 380,000 years old, the CMB carries in its structure the imprint of the early universe, the density fluctuations that would later grow into galaxies and galaxy clusters. The pattern of these fluctuations tells us about the geometry of the universe. One crucial measurement extracted from the CMB is the universe's curvature. General relativity allows for three possible geometries for a uniform, expanding universe. A positively curved universe like the surface of a sphere, extended to 3 dimensions, is spatially finite. A negatively curved universe like the surface of a saddle is infinite. A flat universe with Euclidean geometry is also, technically, consistent with being infinite. Measurements of the CMB by the Planck satellite, published most precisely in 2020, constrain the curvature of the universe to be very close to flat. The measurements are consistent with zero curvature, a flat universe to within approximately 0.5%. A flat universe, in the standard interpretation, is infinite. It extends without bound in all directions. Our observable universe is an extraordinarily tiny fraction of an infinite whole. However, this conclusion that the universe is infinite rests on the assumption that the universe is globally uniform, that the regions beyond our horizon are similar to the regions within it. This is an assumption, not a measurement. We cannot verify it directly, but it is consistent with the theory of inflation, which predicts a very large, likely vastly larger than observable uniform universe, and with the general principle that our location in the cosmos should not be privileged or special. If the universe is infinite, then what lies beyond our horizon is more universe, more galaxies, more stars, more planets. The same physical laws, the same chemistry, the same cosmological history, extending without end. That alone is a thought that deserves some time to settle. The word infinity is used casually in many contexts. An infinite number of possibilities, an infinite variety of outcomes, an infinite capacity for something or other. Casual usage has perhaps dulled the genuine strangeness of what mathematical infinity actually implies. In the context of a spatially infinite universe, infinity is not a large number. It is not a very large number. It is the complete absence of an upper bound. There is no number, however large, that counts all the stars or all the galaxies in an infinite universe. There is simply more, always more, without end. What does this mean in practical terms? If the universe is indeed infinite, and if it is uniformly populated with galaxies at the density we observe within our observable portion, it means that every possible configuration of matter that the laws of physics allow will occur not just once but an infinite number of times. This is not a mystical claim. It is a straightforward mathematical implication of infinite space with finite density of possibilities. If the configurations of matter within any finite region of space are finite in number, even if astronomically large, then in an infinite space, every possible configuration must occur infinitely often. This includes a region of space that is, in every measurable way, identical to our observable universe, including a planet identical to Earth, including you reading or listening to this, having exactly this thought, not metaphorically identical, physically identical, down to every particle. In an infinite universe, there are infinitely many copies of you, infinitely many variations of you. Every decision you have ever made, every path not taken, exists in some volume of this infinite space, realized. Physical, real. This is called the level I multiverse by the physicist Max Tegmark, the most conservative and mathematically direct implication of a flat, infinite universe. It follows from standard cosmology with no exotic additions. It requires only that the universe is genuinely infinite and uniformly populated. The nearest such copy of you would be at an almost incomprehensibly large distance, estimated at 10 to the power of 10 to the power of 119 meters, a number so large that writing it out would require more digits than there are atoms in the observable universe. But in an infinite universe, that distance is not the end of the story. It is just the beginning. The conclusion that a flat universe must be infinite rests on one additional assumption that is worth examining: that the universe has the simplest possible topology, the simplest possible way of being connected to itself. Topology is the branch of mathematics concerned with properties of space that are preserved under continuous deformation. Two spaces can have the same local geometry, the same curvature at every point, but different global topology. The classic example is a flat torus, familiar to anyone who has played a video game where moving off one edge brings you back on the opposite edge. A flat torus has exactly the same local geometry as an infinite flat plane, but it is finite. Wrap around far enough and you return to where you started. A three-dimensional analog, a three-torus, is a universe that is locally flat but globally finite. If you travel far enough in any direction, you return to your starting point. Such a universe would be finite in volume, but have no boundaries, no edges, no walls. Just a universe that loops back on itself. Cosmologists have searched the CMB for evidence of such a topology, looking for repeating patterns that would betray the universe's periodic structure if it were smaller than or comparable to the observable universe. The most direct signature would be pairs of circles in the CMB sky where the same structures appear, mapped from two different directions, because the light that created them originated from the same points seen from different sides of the loop. No confirmed evidence of such circles has been found in the Planck CMB data. This places a lower bound on the size of the universe. If it is toroidal, if the universe loops back on itself, it must do so on a scale larger than our observable horizon. This means that even if the universe has a finite toroidal topology, its volume is larger than the volume of our observable universe. We cannot see all of it. What lies beyond our horizon, even in a finite, topologically closed universe, remains unobservable. The universe may be finite but immensely larger than what we can see, or it may be genuinely infinite. Both possibilities involve a vast beyond that we cannot access. The modern scientific understanding of what lies beyond the observable universe is deeply informed by the theory of cosmic inflation, one of the most successful and widely accepted theoretical frameworks in cosmology, even though it has not yet been directly confirmed by observation. Inflation proposes that in the first tiny fraction of a second after the Big Bang, within the first 10 to the power of minus 32 seconds, a duration with no analogue in human experience, the universe underwent a period of exponential expansion. Space doubled, then doubled again, and again, and again, at a rate vastly exceeding the speed of light. Not matter moving through space, but space itself expanding. This is not a violation of relativity, which limits the speed of objects through space but places no limit on the rate at which space itself can expand. In this extraordinarily brief moment, a region vastly smaller than a proton was inflated to a scale much larger than the observable universe today. The tiny quantum fluctuations present in that initial microregion were stretched to macroscopic scales, becoming the seeds of the large-scale structure we observe today. The temperature fluctuations in the CMB, which seeded the formation of galaxies and galaxy clusters, trace directly back to those quantum fluctuations inflated to cosmic scales. What inflation implies about the universe beyond our horizon depends on how inflation ended. In the simplest models, inflation ended everywhere simultaneously or approximately so, producing a roughly uniform universe of enormous size. In these models, What lies beyond our horizon is more of the same universe we can see. Same physical laws, same cosmological history, just too far away for its light to have reached us. In more complex models that many theorists consider more natural, because they allow inflation to end at different times in different places, something more interesting emerges. Something called eternal inflation. Eternal inflation is not a single theory, but a broad class of inflationary models that share one common feature. Once inflation starts, it never fully stops. In these models, the field that drives inflation, the inflaton field, in technical language does not decay uniformly everywhere. Instead, quantum fluctuations in the inflaton field cause it to decay in some regions while continuing to inflate in others. The regions where it has decayed form what are called bubble universes, regions that exit inflation and begin the hot, expanding evolution that our observable universe has undergone. The regions where inflation continues the vast majority of the volume, because inflating space expands faster than bubbles can form, keep expanding exponentially. In this picture, bubble universes are constantly nucleating, forming throughout an eternally inflating background. Each bubble is causally disconnected from the others. They cannot communicate. The space between them is expanding faster than light, making it impossible for any signal to cross from one bubble to another. Our observable universe, everything we can see, everything we have ever measured, is the interior of one such bubble. The Big Bang was not the beginning of the universe, but the beginning of our bubble, the moment when inflation ended in our particular region and the hot, dense evolution of our universe commenced. Beyond our cosmological horizon lies first more of our bubble, the unobservable portions of our own bubble universe. And beyond that, beyond the edge of our bubble, is the eternally inflating background, seething with quantum fluctuations, nucleating new bubbles constantly, never ending. Each new bubble that forms is, in a meaningful sense, a separate universe, with potentially different physical properties, different particle physics, different constants of nature, different histories. The ensemble of all these bubbles is the multiverse, the level 2 multiverse in Tegmark's classification. If eternal inflation is correct, the multiverse is not merely a philosophical speculation. It is the direct and necessary consequence of the most successful cosmological theory we have. One of the most remarkable implications of the multiverse produced by eternal inflation is the possibility that different bubble universes, different regions of the larger inflating cosmos, may have different physical laws, not merely different initial conditions, but genuinely different physics, different particle masses, different coupling constants, different numbers of spatial dimensions, potentially different structures of quantum mechanics itself. How is this possible? In string theory, the most developed framework for unifying quantum mechanics with gravity, the space of possible physical laws is not a single point, but a vast landscape. The fundamental parameters of physics, the masses of particles, the strengths of forces, the value of the cosmological constant, are not fixed by the theory itself. They are determined by the specific configuration of extra dimensions and fields in a given region of spacetime. Different configurations produce different effective physics. The number of distinct configurations in the string theory landscape is estimated to be astronomically large, perhaps 10 to the power of 500 or more. Each configuration corresponds to a different set of physical laws, a different universe. In the context of eternal inflation, each bubble universe that nucleates may settle into a different configuration of this landscape, a different set of physical laws. The physics we observe is not the unique, inevitable physics of the universe, but the physics of our particular bubble. Other bubbles have other physics, other particle masses, other force strengths, perhaps other numbers of spatial dimensions, though 3 spatial dimensions may be necessary for the kind of complex chemistry and stable planetary orbits that lead to observers. The cosmological constant, the value of dark energy, is particularly interesting in this context. In our universe, the cosmological constant has a value that seems extraordinarily fine-tuned, small enough that it did not prevent gravity from assembling galaxies and stars before the dark energy-driven expansion became dominant, but large enough to be measurable. In the landscape picture, this value is simply the value that our particular bubble happens to have selected from the enormous range of possible values by the fact that observers can only exist in bubbles with values compatible with the formation of galaxies and stars. This is the anthropic principle applied to the multiverse. We observe the physics we do because our bubble has physics compatible with our existence. The beyond implied by eternal inflation, the multiverse of bubble universes, is spatial. It lies beyond our cosmological horizon, in regions of space that are real but unreachable. It is a beyond of geography, of distance, of causally disconnected regions. But there is another kind of beyond that modern physics contemplates, one that is not spatial at all, but quantum mechanical. One that arises not from the large-scale structure of the inflating cosmos, but from the smallest scales of quantum behavior. Quantum mechanics, the framework that governs the behavior of matter and energy at atomic and subatomic scales, is, along with general relativity, one of the two foundational pillars of modern physics. It is extraordinarily successful. Its predictions have been confirmed to extraordinary precision in countless experiments, but it contains, at its core, a feature that has no fully agreed upon interpretation after nearly a century of discussion. When a quantum system is measured, when an observation is made, the quantum superposition of many possible states collapses to one definite outcome. The system, which existed in a superposition of possibilities, becomes one specific thing. The other possibilities apparently vanish. Where do they go? In the many worlds interpretation of quantum mechanics proposed by Hugh Everett in 1957 and taken seriously by a significant fraction of physicists, today they do not vanish. Instead, the universe branches. Every quantum measurement, every interaction that could have multiple outcomes, produces multiple branches of reality, one for each outcome. All branches are equally real. The universe we experience is one branch among an unimaginably vast number, constantly branching with every quantum event. In this interpretation, the beyond is not spatial. It is not accessible by any spacecraft. It is not in a direction. It is a structure of reality that is parallel to ours, branching from shared moments, diverging with every measurement, every radioactive decay, every photon interaction, everywhere in the universe, at every moment. This is the Level 3 multiverse in Tegmark's classification, the most uncomfortable, perhaps, in its implications for identity and continuity, and the most difficult to test. All of the possibilities we have been exploring, the infinite extension of our flat universe, the bubble universes of eternal inflation, the branching worlds of quantum mechanics, share a common feature that places them in a difficult relationship with the scientific method as conventionally practiced. They are, in their fullest forms, untestable. Not untestable in the sense of merely difficult to test, the way that the existence of a black hole's singularity is difficult to test because we cannot survive the journey to it. Untestable in a stronger sense. The other bubble universes are causally disconnected from ours by construction. No signal can reach us from them. No observation we can ever make will directly confirm or deny their existence. The other branches of the many worlds interpretation are orthogonal to ours in Hilbert space, the mathematical space of quantum states, and their contents are, by construction, unobservable from within our branch. This has led some physicists and philosophers of science to argue that these multiverse concepts are not science at all, that they are metaphysics or mathematical philosophy, but not empirically testable physics. The physicist David Gross has expressed skepticism. The philosopher Jim Baggott has argued for what he calls a farewell to reality, the concern that physics has moved beyond what can be empirically tested. Others disagree. The physicist Max Tegmark argues that untestability is not unique to multiverse theories, that all of physics makes claims about things that are not directly observed, and that the criterion should not be direct observability, but logical consistency and explanatory power. Sean Carroll argues that the many worlds interpretation of quantum mechanics is not a speculation added to physics, but the most straightforward reading of the mathematics of quantum mechanics, that branches happen whether or not. We call them universes. The debate is genuine and ongoing. It is one of the most interesting conversations at the intersection of physics and philosophy. What all parties agree on is that these ideas cannot be confirmed by any observation currently available or foreseeable. They are the logical consequences of our best theories, taken seriously extrapolations from confirmed physics into regimes that no instrument will ever reach. Whether that makes them science or philosophy depends on how you define the terms. What it does not change is the fact that they are real possibilities, grounded in real physics, that deserve to be taken seriously. One of the most interesting philosophical questions raised by the multiverse in any of its forms is why we find ourselves in a universe with the particular physical laws and constants that we observe. The constants of physics, the strength of gravity, the mass of the electron, the charge of the proton, the value of the cosmological constant appear, when examined carefully, to be extraordinarily fine-tuned for the existence of complexity. Small changes in any of them would produce a universe radically different from ours, and in most cases, a universe in which stars cannot form, or complex chemistry cannot occur, or atoms cannot exist. This fine-tuning is a genuine scientific puzzle. Why do the constants have the values they have? Are those values uniquely determined by some deeper theory we have not yet found? Or are they, in some sense, selected from a range of possibilities? In the multiverse framework, the answer to the second question is yes. They are selected, but not by any external agent or design. They are selected by the fact that we exist to ask the question. Of all the bubble universes in the multiverse with their range of physical constants, only those with constants compatible with the existence of observers will contain observers to wonder about their constants. We find ourselves in a universe with life-compatible constants because we could not find ourselves anywhere else. This is called the anthropic principle, or more precisely, the weak anthropic principle. It is a straightforward logical observation. The conditions we observe must be compatible with our existence as observers, because if they were not, we would not be here to observe them. The anthropic principle does not explain why the multiverse exists. It does not explain the laws of physics, but it provides a framework for understanding why, in a multiverse of many possibilities, we find ourselves in a particular region with particular properties. And it connects the vast, cold, impersonal physics of bubble universes and eternal inflation to something very immediate and very personal. Why are you here? Why is there something rather than nothing with these particular laws in this particular universe? One possible answer, because in a multiverse of enormous variety, you could only be in a version that could contain you. At the furthest frontier of what serious physicists and mathematicians have contemplated beyond the spatial multiverse, beyond the quantum branches lies an idea that is either the deepest insight in the history of human thought or the most ambitious overreach. It is called the mathematical universe hypothesis, developed most fully by Max Tegmark, and it proposes something radical, that the universe does not merely follow mathematical laws, it is mathematical structure. Not described by mathematics, it is mathematics. In this view, there is no distinction between a mathematical structure and a physical universe. Every consistent mathematical structure that can be formally defined is, in some sense, a real universe. The reason our universe obeys mathematical laws so precisely, the unreasonable effectiveness of mathematics in describing physical reality, as the physicist Eugene Wigner famously called it, is not a mystery. It is because our universe is a mathematical structure. The beyond in this framework is not just other bubbles or other quantum branches. It is all possible mathematics, every geometrical structure, every algebraic system, every consistent formal system that can be described. Each is, in some sense, as real as our own universe, though most are so simple, or so complex, or so structurally different from ours, that they contain nothing analogous to matter, space, time, or observers. We exist in the particular mathematical structure that supports our existence consistent with the anthropic principle at its most extreme expression. This is, by any measure, an extraordinary idea. It is also genuinely unprovable in any conventional scientific sense. It is philosophy of physics at its most ambitious and most speculative, but it is worth knowing about, because it represents the logical endpoint of taking mathematics seriously as the language of reality, asking not just what the equations of physics describe, but what they are. We have been exploring ideas of enormous abstraction, infinite universes, bubble cosmologies, branching quantum realities, mathematical structures. Let us pause and ask what it means, emotionally and philosophically, to hold these ideas, to genuinely sit with the possibility that our observable universe is one of many, perhaps one of infinitely many with no privileged status among them. There is an initial reaction that many people have to these ideas that resembles diminishment. If our universe is one of countless, if the physical laws that govern us are merely the particular values our bubble happened to settle into, if every possible version of every possible event is realized somewhere in the quantum branches, then what is unique? What is significant? What grounds the sense that our particular universe, our particular lives, our particular choices and experiences matter? This reaction is worth taking seriously. It is honest, and it points to something real. But there is another way to hold the ideas, one that finds in them not diminishment, but a kind of extraordinary privilege. We are in this universe. We observe these laws. We experience this particular set of physical constants that allows for stars and chemistry and biology and thought. Whatever the multiverse contains, whatever other bubbles exist with whatever other physics, none of it changes the reality of this universe. These laws, this experience. A painting does not become less beautiful because other paintings exist. A moment of joy does not lose its quality because other moments exist elsewhere. The fact that other versions of reality are instantiated in some vast mathematical or physical structure beyond our horizon does not diminish the reality or the significance of what is here. If anything, the multiverse picture should deepen our appreciation for this particular universe, the one that happened to permit us, the one we are in, the one that, of all the possibilities, contains this moment. Throughout human history, every culture has confronted the limits of what it can know. The darkness beyond the campfire, the horizon at sea, the sky at its zenith. In every era, those limits have carried a mixture of discomfort and wonder, the discomfort of not knowing, the wonder of contemplating what might be there. Our era is unusual in having extended the limits of knowing further than any previous era could have imagined. We have mapped the observable universe to its horizon. We have characterized the CMB to extraordinary precision. We've detected gravitational waves from colliding black holes, 1 billion light-years away. We've imaged the shadows of black holes. We've analyzed the atmospheres of planets orbiting other stars. And still, there is more beyond what we can see than what we can. The observable universe, for all its vastness, may be an infinitesimal fraction of what exists. The limits of human knowing have not shrunk with our expanding instruments. They have grown. The further we reach, the more clearly we can see how much further there is to reach. This is not a discouraging pattern. It is the most honest description of the relationship between minds and the universe those minds inhabit. The mystery of what lies beyond our horizon is not a failure of science. It is science's most honest achievement, the precise identification of what we do not and cannot know, and the rigorous exploration of what the physics of what we do know implies about the unknowable. There is a particular kind of comfort available in this, not the comfort of answers, but the comfort of honest questions. The recognition that the universe is larger than our knowing is, paradoxically, one of the most grounding recognitions available to a curious mind. We are here. We have instruments. We have mathematics. We have the capacity to think carefully about the most difficult questions in existence. And we have reached the edge of what those instruments and that mathematics can confirm and looked past it with the best tools we have and found that there is more. Always more. Even though the beyond is, by definition, beyond direct observation, there are things we can learn from observations within our horizon that will constrain what lies beyond it. The geometry of the universe, measured with increasing precision from CMB observations and galaxy surveys, will continue to constrain the size and topology of the universe. If the universe is not precisely flat but has a slight positive curvature, this would imply a finite volume and measurements precise enough to detect that curvature would set an upper bound on the total volume. Current measurements are consistent with flatness to very high precision, but not to infinite precision. Future experiments, the Simons Observatory, the CMB, S4 experiment, will further tighten this constraint. The CMB itself, examined for the topological signatures of a small universe, the matched circles that would appear if the universe wraps back on itself at a scale comparable to our observable horizon, has been searched extensively without confirmation. Future CMB experiments with higher sensitivity may detect fainter topological signatures if they exist, or tighten the lower bound on the universe's size if they do not. The large-scale structure of the universe, the distribution of galaxies on the largest scales, also carries information about the universe's global properties. Anomalous features in this structure, if confirmed, could hint at processes that occurred beyond our current horizon and left imprints on the observable universe through their influence during inflation. Gravitational waves provide another window. The primordial gravitational wave background, a faint stochastic signal expected to have been produced during inflation, encodes information about the inflationary process. Its detection and characterization would constrain which models of inflation are correct and therefore what kind of larger universe inflation produced. None of these observations will directly reveal what lies beyond the horizon, but they will sharpen the theoretical framework, telling us more precisely which version of the multiverse, or which version of inflation, best fits the observable universe. And from that framework, more precise statements about the beyond become possible. There is a category of question, perhaps the most important category that science can approach but never fully resolve. Not because of limitations in our instruments or our mathematics, but because of the fundamental structure of the situation. Questions about what lies beyond causal horizons fall into this category. We will never directly observe another bubble universe. The causal disconnection is not a technological barrier, but a physical one built into the structure of spacetime by the expansion of the cosmos. We will never verify the branching of quantum realities. The many worlds interpretation is, by design, empirically indistinguishable from its alternatives when it comes to the unobservable branches. We will never confirm or deny the mathematical universe hypothesis through any experiment. And yet these questions do not become less important because they are unanswerable. If anything, they become more important. The permanently open question is not a lesser kind of question, it is the deepest kind. The permanently open question is what our descendants will inherit from us, not the answers we found, which will be refined and extended and eventually superseded, but the questions we formulated with enough precision to know that they are genuinely hard. The framework of ideas within which the beyond is not merely undefined darkness, but a structured, mathematically characterized possibility space. That is a genuine gift from one generation to the next. The precise articulation of what we do not know, what lies beyond the observable universe, should not terrify us. The word in the title is chosen for its marketing value to suggest a confrontation with the extreme, a face-to-face with something overwhelming. But the honest response to the beyond is not terror, it is wonder. Deep, sustained, genuine wonder at the possibility that everything we can see, the 2 trillion galaxies, the 100 trillion stars in our galaxy alone, the 500 billion potentially habitable planets in the Milky Way, the entire observable universe with its 46 billion light-year radius, is a bubble in something incomparably larger. That our physics, our chemistry, our biology, our consciousness may be the particular expression of a tiny corner of a vast, diverse cosmos that extends in space, in quantum branches, in mathematical structure, without any end, we can reach or measure. There is an exercise that physicists sometimes recommend to students encountering the multiverse for the first time. Not a mathematical exercise, simply a contemplative one. Sit with a number. Not any specific number. The exercise is about the quality of the infinite, about genuinely trying to hold, for a moment, not a large number, but the absence of an upper bound. The recognition that in a truly infinite universe, there is no largest galaxy, no farthest star, no outermost bubble. There is always more, always further, always another level. Most minds, when they first try this exercise, feel something that resembles vertigo, a kind of cognitive slip. The mental footing gives way for a moment, as the normal reference points of scale and comparison fail. The universe is bigger than can be compared to anything, because anything available for comparison is inside it. And then if you stay with it, rather than retreating to the comfortable finitude of everyday scale, something else sometimes happens. The vertigo settles. The mind, unable to grasp the infinite as a concept, relaxes its grip, and in that relaxing, something opens. A recognition of proportion that is more accurate than the distorted proportion of ordinary experience. A momentary awareness of the true size of the cosmos, and the true size of our concerns within it. Not the anxious smallness of feeling insignificant, but the peaceful smallness of knowing one's place within something genuinely immense, and genuinely indifferent, and genuinely ancient. This is what the beyond offers, ultimately. Not answers, not confirmation of the theories, but the experience of genuinely contemplating the limit of what can be known, and finding that the limit, approached with honesty and patience, is not a wall, but a threshold. Beyond it, not nothing, but everything we cannot see. 46 billion light-years in every direction. That is the edge of what we can see. The boundary of the observable universe. The horizon beyond which no light has had time to reach us. Beyond which no information from the first 13.8 billion years of cosmic history has yet arrived. Right now, at this moment, while you listen to these words, photons are travelling toward us from regions of space that are, at this instant, approximately 46 billion light-years away. They have been travelling for nearly the entire age of the universe. They carry the oldest light we will ever receive from that direction, the light of the hot, dense early universe, stretched by the expansion of space to the longest radio wavelengths. And beyond those photons, beyond the regions from which they came, the universe continues. If inflation is correct, it continues for distances that are incomparably larger than our observable bubble. If eternal inflation is correct, it continues into an inflating background where new bubble universes nucleate constantly, each with potentially different physics, different laws, different histories. If the universe is flat and infinite, it extends without limit, repeating every possible configuration of matter and energy an infinite number of times. If the many worlds interpretation of quantum mechanics is correct, every quantum measurement branches our reality into a proliferation of parallel versions in which every possibility is realized, every path taken, every outcome instantiated. If the mathematical universe is correct, every consistent mathematical structure is real, and ours is simply the one we find ourselves in, the one compatible with our existence, one of an uncountable number of self-consistent formal systems, each instantiating its own form of reality. We do not know which of these is true. We may never know. The beyond is, perhaps uniquely among all the frontiers of science, permanently beyond the reach of direct verification. But it is there. The universe does not end at our horizon. It continues. It was continuing before we had eyes to see any of it. It will continue long after the last light from the most distant stars has faded, long after the observable universe has grown dark and cold. The beyond does not wait for us to look at it. It does not need our observation to be real, and this the recognition that reality is vastly larger than our perception of it, that the cosmos is richer and stranger and more various than any description we can make, is not, ultimately, a source of terror. It is the universe's greatest gift to a curious mind, the gift of inexhaustibility, the gift of knowing that however far we reach, however carefully we look, however precisely we measure, there will always be more, always a deeper question, always a larger context, always another level of structure waiting beyond the level we have just understood. We are small, we are brief. We live in a bubble of a bubble of a bubble of something beyond all our ability to fully comprehend. And we are here, aware of it, grateful for the portion we can see, wondering, quietly and without end, about the rest. Thank you for travelling with us tonight to the edge of everything, for sitting with the infinite not to grasp it, not to conquer it, but to let it be as large as it actually is, and to find in that largeness not fear, but the deepest possible form of wonder. Beyond the observable universe, something continues, vast, ancient, quiet, real, and entirely, peacefully beyond our horizon.